Okay, kiddos, so this is going to be your lesson 14-13 instructional video, and we're going to talk about the basics of polynomials here, and it seems like we're covering a lot, but a lot of it is stuff you already know and or stuff that you briefly went over in Algebra 1 to begin with. So here's our essential questions. So we're going to talk about why we have to restrict a function's domain in certain situations. We're going to talk about what a polynomial is in general, what the degree of a function or polynomial is, what the relative minimum or maximum of a polynomial, or I should say not of a polynomial, but of a function is, and what end behavior is. Okay, so let's start with EQ1. So why do we have to restrict a function's domain given a certain situation? So here we've got a situation. So the U.S. Postal Service will not accept rectangular packages if the perimeter of one end of the package plus the length of the package is greater than 130. So let's go ahead and start breaking this down and try to understand what they're saying. So if the perimeter of one end of the package plus the length is greater than 130. So what this means is they will accept it so long as the perimeter, so that would be W plus W plus W plus W, so that would be 4W, plus the length, right, plus the length is less than or equal to 130, and we're talking about inches if I remember, inches, right? But just to go ahead and make this simpler, let's not deal with inequalities. Let's deal with actual equations. So we can go ahead and just say that the perimeter can be expressed in this way, that 4 times the width, or W plus W plus W plus W, plus the length, we can go ahead and just say that it's got to be equal to 130 inches. That way we don't have to mess with an inequality, and we know that the U.S. Postal Service will still accept it. Okay, so we're already looking at the picture, which is the next part it wants us to do. Let's go ahead and look at problem number 1. So what's the largest possible volume for an acceptable rectangular package? Well, without looking at a graph of this as a function, we can't really tell, but we can estimate if we just kind of, throw some numbers around. So right here, what happens if the width is 10? Well, based on what I've got over here, right, if the width is 10, well, that would end up being 40 for the width, or for the perimeter of the end, plus a length that we don't know, but it has to add to 130. Okay, so that means that would be 40, plus it would have to be 90, and that gives us the 130. Now, what would our volume be in this case? Well, that means our width is 10, right? Our height, which is also our width, would also be 10. And our length would be equal to 90 like we just saw. So our volume would be 10 times 10 times 90, right? And from that, we would get 9,000. Okay, so you kind of see where we're going with this table if we just throw some numbers around. As long as we stick within the parameter that the perimeter, right? So this is the perimeter. So long as the perimeter is equal to 130 inches, right, then we're good. Okay, so the largest possible, and I'm not going to go ahead and actually calculate this hand by hand. The largest possible, as far as this table is concerned, would be here at about 20,000. So somewhere around there is the largest possible volume. So given the info, write an equation for the length of the package as a function of W, the width. So we already are halfway there. We can just use this. Okay, so if we say length as a function of width, all we have to do is solve this guy here for L. And we can do that simply by subtracting 4W from both sides. So we end up with the length is equal to 130 minus 4 times the width. Okay, so let me go ahead and erase this. So what I can go ahead and do is say that our length can be defined in terms of the width as 130 minus 4W. Okay? So that was number 2. Number 3, write the volume of the package as a function of W. So that would be W times length. Okay, so what we end up with is volume as a function of width is equal to W times W, or W squared, times our length, which is 130 minus 4W. Okay? Number 4, graph your function and determine the appropriate domain and range for it given the scenario. Okay, so now I'm going to have to take this and basically input it into Desmos here, which is what I'll go ahead and do. And my little window's off a little bit. But instead of using W, I'm going to go ahead and use the letter X. So X, and if I do Shift 6, it gives me the option to input a exponent. So I have X squared, that's our W squared, times 130, oops, 130 minus our W, or X, right? And we get something a little bit crazy looking. Okay, so even if we zoom out, we can't really see anything of what's going on. So we're going to have to jack with the settings a little bit. And it's useful that we already know that our maximum volume is around 20,000, right? So I'm going to say for my y-axis, I'm going to say negative 1,000 to about, we'll call it 22,000. Okay, and I goofed whenever I did this. That should be 4x, right? Minus 4x. Let me make sure I wrote that down. Yeah, okay. Whoopee! Okay, so now that fits. Okay, so now our picture's not so stupid looking. And I can go ahead and do this. And, well, what do we see? And actually, I can go ahead and adjust my x. So let's say from, we don't need it to be that far, negative 10, let's say to 34. Let's click off to the side here. So you notice that our graph, well, let's think of it this way. Okay, so our y-axis, and I can go ahead and give it labels, so that way you have the visual. So our x-axis is our width, and our y-axis is our volume. Okay, so looking at our axes, right? Well, we see we can't have a negative width. Okay, we can't have a width sitting out here because that's just ridiculous. Okay, unless we're going into like the upside down or something, right? And we can't, so you notice we go off below here, we can't have a negative volume, right? Because that would imply we have like negative mass or something, and that's getting into like Star Trek. Okay, so why do we need to restrict the domain of functions given certain situations? Well, it's simple in this case because physically, right, if we have a physical object, that physical object cannot have anything less than 0 for any of its measurements. So that's why our domain must be from 0 over here to our x-intercept. And I'll go ahead and print that out right there. So our x-intercept, obviously, Desmos is freaking awesome. Our x-intercept over here on the right is 32.5. So our domain must be 0 to 32.5. So I'm going to go, and we're going to be inclusive, right? So our domain, I'm just going to do that. Our domain is given by 0 to 32.5, okay? And if we're using inequality notation, we would say 0 less than or equal to our width less than or equal to 32.5. Well, what about our range? So let's go back and look here. So what would our range be? Well, that's given by our relative maximum here, and we'll talk more in depth about what relative maximum is here later in the video. But we're going again from 0 all the way up here to 20,342.59. So we're going from, so I'm going to do range, we're going from 0 to, I already forgot, it was 20,000, let me look again, 20,342.59, can barely fit it in there. Anyway, so if I do the inequality notation, so it's going to look a lot like what we had for the range. So 0 is less than or equal to our volume, is less than or equal to the 20,342 0.59. I'm just going to leave the decimal off. Not that important. So what is our maximum volume? Well, we just saw our maximum volume is given by this upward bound of our range. Okay, so our maximum volume is simply the 20,342.59 cubic inches, right? And if you remember from geometry, if we're doing volume, that's a three-dimensional measure of space, so we're using cubic units. And what width is this maximum reached at? Okay, so our width we're reaching this at is 21.67 inches for our width. So we would just say our maximum width, or I shouldn't say our maximum, we should say our optimal width, right? Our optimal width is at, and I already forgot, I'm getting too wordy, 21.67 inches. Okay, and we would just leave it linear inches there in that case. Okay, so pretty straightforward how this all works. And here we see our graph that we were just looking at a second ago. Okay, so here, and I can actually write on this one, so here is our two x-intercepts. Okay, and they represent where our volume is 0. Okay, and here is our maximum. And it's not our absolute maximum, it's our relative maximum. And again, we'll talk about that here later. Okay, and it's where our maximum volume is at a width of 21.67 inches, just like we talked about. Okay, so just a whole lot of applying this stuff, really. None of this is really that new or that difficult. Okay, so what's new is the concept of something called a polynomial. Okay, so a polynomial, basically, if we give it in standard form, looks like this. So ax to the n plus bx to the n minus 1 plus cx to the n minus 2, and so on and so on and so on. Okay, so what ends up happening is we have n decreasing from left to right, right? Meaning we have n decreasing in descending order, or we're writing it in descending order. Okay, so the other thing, here furthest to the left, we have our highest degree term. Okay, and this a right here is our leading coefficient. Let's see if I can spell. Okay, and let's say, you know, at the very end we have d times x to the 0, right? Well, x to the 0, this would just be 1. That's just equal to 1. And the d would just be a constant, therefore. Okay, so that was very generalized and ambiguous. Let's look at something a little more specific. Okay, so here's an example of a polynomial right here. Okay, and we see that its highest degree is 5. So this is a 5th degree polynomial. Okay, and you'll see here over in this cute little table here, right? So the name of the polynomial changes depending on the highest degree. So if we have a degree, the highest degree of the polynomial is 0, it's called a constant polynomial, or it's just called a constant. Okay, if it's to the first degree or the first power, it's linear. So an example of that would be your basic y equals mx to the first power, right? It's understood that that's a 1. Y equals mx plus b. Okay, so that would be your linear equation or your linear function. Okay, then you have quadratics, which we know all too well about. I'm trying to find the right color here. So quadratics. So f of x equals x squared plus 2x minus 5, something like that. This would be quadratic. Well, then you've got your cubics, which we should know pretty well by now also. So f of x equals x to the third minus 4x squared plus 2. I don't know. The point is the highest degree on a cubic is to the third, right? And you can already guess a quartic, your highest degree term would be a 4. This guy here would be quintic because we have a fifth degree as the highest term. And we see that we have a leading coefficient of this polynomial as 7, okay? And some notable attributes are given here on these little bullet points. So the first one, the constant term of a polynomial is typically, and pretty much always, going to be your y-intercept. Okay, the constant term is your y-intercept of the graph. Okay, second thing, the highest degree term, right? So in this case, the 5, the highest degree term tells the maximum number of x-intercepts, aka roots. Okay, and we'll get into that a lot deeper as we progress further into the unit, that the graph of the polynomial can have. Okay, so if this is a fifth degree polynomial, that means that it can, at a maximum, intercept the x-axis, excuse me, it could intercept the x-axis 5 times. So a quadratic, if you remember, a quadratic, okay, so this is just an example, it's an upside down parabola. Well, it has a maximum of 2 roots or 2 x-intercepts. Okay? So that fifth degree polynomial up there can have a maximum of 5. All right, so the degree of the polynomial gives you information about the shape of the graph at its ends. And again, if we talk about quadratics and polynomials, both of which we're familiar with now, so a quadratic is going to be shaped like a parabola, right? A cubic is going to be kind of like I'm trying to think of the best way to describe a cubic. It's going to look something like that. Okay? So we already have that down. Just like we know square root functions are going to look like this, more or less, sideways half parabolas. Cube roots are going to look like this guy that we just drew, except, sideways. Okay, so you get the idea, right? Okay, so coming back to the rest of the lesson. So let's go ahead and answer EQs 4 and 5. So what is a relative minimum or maximum, and what is end behavior? So before we get into that, let's revisit what we were just talking about. So let's revisit this graph here, and I'm going to go ahead and copy and paste something real quick. Be a little faster for me. So let's revisit the volume function from all this nonsense over here when we were talking about the Postal Service package, right? So let's look at our graph again of that. So here is our function from earlier, except I've just zoomed it out a little bit, and it's written pretty ugly, right? But I can go ahead and do this, and even though it's not taking it, I can just rewrite it. I at least have it there to copy. If you ever need help entering stuff into Desmos, or you're still not sure how it works, let me know. But as we can see, right, whether blue or red, these both are equal because they overlap one another. They run exactly the same thing. They're the same function. Okay, so I'll just leave it here on the blue. But let's look at, on this next page here, let's look at some little attributes that we've got. Okay, so let's answer EQ 4 and 5 relative to this function here. And of course, we're looking at this guy here, f of x. This was our function of volume, or our function for volume. Okay, so this y-axis was the volume, and the x-axis was the width. Okay, here we have our x-intercepts at x equals 0 and at x equals 32.5. Okay, and here, and I mentioned this earlier, this is our relative maximum. Why do we say it's our relative maximum? It's not our absolute maximum, okay? We know that this guy goes on and on and on and on and on. It's not ever going to really stop. and even going down, right, it's never going to stop going down either. Okay, so we say it's our relative maximum because it's our maximum relative to the situation, whether or not the Postal Service will accept it. Okay, so it is our relative maximum. All right, so in that same light, what would our relative minimum have to be? Well, our relative minimum is simply 0. And we see very clearly, that's not the absolute minimum, right? It continues down here to negative infinity, okay? But relative to our problem, right? Again, talking about the Postal Service, that it's a physical object, okay? Our relative minimum is simply 0, right? So now let's talk end behavior. So let's not talk about the physical aspect of this anymore. So let's pretend this had nothing to do with the postal package. Let's pretend this was just a function of x, some unknown x, right? Well, what we would simply say is that x, as it approaches, and that's what this arrow means, okay? I'm saying as x approaches. So if I say x approaches infinity, and if there's no minus sign, I mean positive infinity. So going on and on and on forever to infinity to the right. What happens as x approaches infinity? As x approaches infinity, we see that f of x approaches negative infinity. And we see that very clearly down here with the arrow I drew earlier. Okay, so as x approaches infinity, f of x approaches negative infinity. Well, what about as x approaches negative infinity? So this would be our left end behavior, right? Over here is negative infinity in the x. So as x approaches negative infinity, what do we see about f of x? Well, f of x goes on and on and on to positive infinity. So as x approaches negative infinity, f of x, or y, approaches positive infinity. Okay, so that would be our left end behavior. So this would be our left end behavior, right? And this guy here would be our right end behavior. Okay, because that's us going to positive infinity, or right, and the left end is called left end because we're going to negative infinity, or to the left. All right, so let's look at an even more abstract example. So this has nothing to do with anything. It's just an abstract example. And again, I'm going to go ahead and just copy and paste this here, and we're going to answer the same two questions. Okay, so what are the relative extrema, or minima, maxima, and what is the end behavior like? So I'm going to enter this into Desmos real fast and see what it is that we get. It's not going to take it because it's stupid, so I have to retype it. Minus 5x squared minus 4x plus 12. Okay, so now that I've got that, so what is it that we have here? So let me zoom out. And that looks kind of ugly. Let's change our x-axis to just fit between -5 and +5. So -5, +5. And our y-axis, so now that I've got that, whoa, I think I made that worse. Oh, cool, it just changed it, even though I didn't want it to. That's just great. Thank you, Desmos. So we're just going to limit y to, I don't know, let's try. Oh, that's what it is. I'm doing the wrong thing. I'm typing, so I'm wanting to type for x, and I'm putting it into y. So -5 to +5. There we go. That's a lot less stupid now. So let me do this, do that. There we go. Okay, I think that's as good as it's going to get. Anyway, so what we see here is very clearly, okay, as x approaches positive infinity, so our right end behavior, okay, our right end behavior is that as x approaches infinity, f of x approaches positive infinity. As x approaches negative infinity, so our left end behavior, as x approaches negative infinity, f of x approaches negative infinity also. Okay, so let's look at a less stupid picture of this. So here we go. This is a nice, prettier one. Couldn't get it to work for me a second ago. But here we see a whole bunch of things. So here's our x-intercepts, right? And our x-intercepts, depending on the context of the problem, our x-intercepts are going to be negative 1.5 and 2. And depending on the context of the problem, these would serve as our relative minima. And that's plural for minimum, right? Instead of saying minimums, we say minima. Anyway, so what about our other numbers here? So here's another key number. So this would serve as our relative maximum. Okay. Now our absolute would be plus or minus infinity for the maximum and minimum respectively. Okay, and then here we see our y-intercept. Okay, and again, that number can be important depending on the context of some situation that this problem is given to represent. But we weren't really given one, so all we need to know is that our relative minimum are equal to our x-intercepts, so that would be negative 1.5 and 2. And our relative maximum would be right here at x equals negative 1/3, which is what this repeating 3 is. And this would be our maximum y value, or our maximum f of x, okay, at that given x, negative 1/3. Okay, so that covers everything. So if you have any questions, obviously let me know. This should cover everything that you need to get the lesson practice done. Come through tutoring or shoot me an email if you have any questions. Otherwise, goodbye.